Why do we learn mathematics? Mathematics is the study of calculation, application, and inspiration. Mathematics is the science of patterns, and we study it to learn how to think logically, critically, and creatively. But too much of the math that we learn in school is not effectively motivated. And when our students ask, why are we learning this? We're often told that it's for a future test or an upcoming math class. But wouldn't it be great if every once in a while we did mathematics simply because it was fun, or beautiful, or because it excited the mind? And I know many people have not had the opportunity to see how this can happen, so let me give you a quick example with the Fibonacci numbers. Now, these numbers can be appreciated in many different ways. From the standpoint of calculation, they are easy to understand as 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and 5 plus 8 is 13, and so on. Fibonacci was actually named by Leonardo of Pisa, and these numbers appear in his book Liber Abaci, which taught the Western world the methods of arithmetic that we use today. In terms of applications, Fibonacci numbers appear in nature surprisingly often. The number of petals on a flower is typically a Fibonacci number, or the number of spirals on a sunflower or a pineapple is usually a Fibonacci number as well. In fact, there are so many more applications of Fibonacci numbers, but what I find most inspirational about them are the beautiful number patterns they display. Let me show you one of my favorites. Let's take a look at the squares of the first few Fibonacci numbers. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared is 25, 8 squared is 64, and so on, right? So when you add consecutive Fibonacci numbers, you'll expect to get the next Fibonacci number, right? Because that's how they're created. But check this out. 1 plus 1 is 2, 1 plus 4 is 5, 4 plus 9 is 13, 9, 25 is 34. And yes, the pattern does continue. In fact, here's another one. Suppose you wanted to look at adding the squares of the first few Fibonacci numbers. So 1 plus 1 plus 4 is 6, add 9 to that, we get 15. Add 25, we get 40. And add 64, we get 104. So these look like regular numbers, but they're actually Fibonacci numbers in them. If you take a look, 2 times 3, 3 times 5, 5 times 8, 8 times 13, 2, 3, 5, 8. These are Fibonacci numbers. Now, as much fun as it is to discover these patterns, it's even more satisfying to understand why they're true. Let's take a look at the last equation. Why does all of that equal to 8 times 13? So to show you, I'll use a quick picture. So first I'll start off by drawing a 1 by 1 square. And then next to that, another 1 by 1 square. So now this is a 1 by 2 square. And under that, a 2 by 2 square. And beside that, a 3 by 3 square. And under that, a 5 by 5 square. And beside that, an 8 by 8 square, creating one giant rectangle. Now let me ask you a simple question. What's the area of the rectangle? Well, on one hand, it's the sum of the area of the squares inside it, right? It's 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared, right? That's the area. But on the other hand, it's a rectangle, and that means the area is equal to its height times its base, and the height is clearly 8, and the base is 5 plus 8, which is the next Fibonacci number, 13, right? So the area is also 8 times 13. Since we've correctly calculated the area 2 different ways, they have to be the same number, and that's why the squares of 1, 1, 2, 3, 5, and 8 add up to 8 times 13. Now if we continue this process, we'll generate rectangles in the form 13 by 21, 21 by 34, and so on. Now I show you all of this because this is beautiful. Like all of mathematics, there's a beautiful side to it that I feel doesn't get enough attention. We spend lots of time learning about calculation, but not forget about application, including perhaps the most important application of all, learning how to think. Without using our brains, without thinking, we would have never found the Fibonacci sequence and all these patterns in the Fibonacci numbers. Very interesting, but without thinking, we couldn't have found them. So if I could summarize this in one sentence, it would be this. Mathematics is not solving for X, but it's solving for Y.